I hope what you're looking at here is familiar from last year. We've got three different forms for quadratic functions. We've got vertex form, and then this one I'm calling root form, and then this one is standard form. And these special forms are special because the parameters p and h and k each have a specific graphical meaning that's easy to interpret, which is not true of all of the parameters in standard form. So, for example, in vertex form, the h you can imagine as a horizontal translation, and the k is a vertical translation. So, without the h and the k, it would be like taking the regular just y equals x squared parabola, and then you add these two translations to take the vertex to h comma k. And then once those are fixed, you can imagine different values of p creating different scale factors that would create a whole bunch of different parabola that all go through that same vertex. So you can see here in Desmos, I've given it a vertex of 3, 4, but then as I shift the p slider, all of these different parabola share that same vertex in common. For root form, each of these linear factors gives a root, which also gives an x-intercept. So you have your two roots at r1, r2, but then, just like before, p is giving you a vertical scale factor that would create a whole bunch of parabola that went through those two roots. So again, on Desmos, you can see here I've got roots of 1 and -2, which you can see here and here. And then as I slide the p slider, you get a whole bunch of different parabola that all go through those two roots. Last is standard form. In standard form, actually, we do know how to interpret that last parameter. We know that that's the same thing as the vertical shift, which is the same thing as the y-intercept. So you can see as I shift the c slider, nothing's changing about the shape of the parabola except the y-intercept. So it's really just shifting it up and down. But if I change the other two parameters, it's not really obvious what they're doing. So here for b, it's moving it somehow, but it's not moving it horizontally or vertically. It's doing both, and it's not kind of clear. And then for A, it seems to be doing this crazy, I don't even know how to describe it. So for standard form, C has an easy to interpret meaning, but A and B may not be so obvious. Okay, so let's say we had 2 points, and I want you to fit some parabola. Let's do the kind of regular algebraic thing. Let's choose one of the forms, we'll plug in some information we know, and then we'll solve for the information that we don't. So two particularly easy parabola to think about would be what if this was the vertex, or what if that was the vertex? If this is the vertex, it's easy enough to plug in the information we know to vertex form, because that's what it was invented for. But depending on the value of p, the parabola might not go through this point. It might do all kinds of things. So you can see in Desmos, I've got the vertex form so far. I've got a vertex at 4, 7. And you can see the point that we want to go through at 10, 0. Right now, my p-value is -0.76, and you see that the parabola is kind of scaled too far. So as I change my p-value, I'm getting closer and closer to the point that I want to go through, but then I pass it. So all of this is to say that you want to solve for the scale factor that will create just the right stretch to force your curve through the point that you want to force it through. So that's what I mean by solve for what you don't know. But I think it's nice to be able to imagine it visually, be able to imagine this infinite family of different curves that all share the same vertex. And then what you're doing when you're solving for a number is picking out the one that makes it do what you want it to do. So doing the actual solving is easy enough. We've already used this point, so let's plug in the other point we know, because we know that by plugging in the x, y values, we're essentially telling this equation we need it always to be true that when x is 10 and y is 0, this remains the same. This remains true. So you can easily solve for p. Here we go. Okay, I forgot to put in the 10 last time. So when the x-coordinate is 10, we get 36 as 6 squared. And then if we solve for p, we've got -7/36. All right, what would it look like if we wanted to make 10 be the vertex? It's the exact same process. I plug in the x and the y coordinates for the vertex in vertex form, and then I plug in the other point to solve for p. So here I've plugged in 7 and 4. And if I'm going to solve for p, it's going to end up being very much the same. So this is 6 squared is 36, and that gives me p equals 7 divided by 36. So you might notice that that's very similar to what we had on the other side here. It's not an accident, and I think maybe if you think about it, you might see why. If you look at these two parabola, you'll see that they have the same exact shape. They have to have the same shape. And we could get from this parabola to this other one just by reflecting it and shifting it. So we don't have to change the scale at all to transform one into the other. So the fact that we can transform one into the other just by flipping and scaling is what tells us that the scale factor only flips. It goes from negative to positive. And then the vertex changes, that's the shifting. But the actual magnitude of the scale factor doesn't change because of the symmetry here, because it's the same shape parabola that you'd need to go from here to there as to go from here to there. So if you'd spotted that symmetry to begin with, you wouldn't have needed to go through this whole solving process. You could have just rewritten this directly over here. Just to show you how flexibly you can think about this, let's choose a different form. Let's choose root form. And I did that because I noticed that this is a root. So let's make R1 be equal to 10, and that gives us this. One thing you could do next would be just choose any other root and then solve for whatever vertical scale factor will force your curve through this other point that we want. So for example, let's choose a root that's quite close. Let's choose 11, 0. So then we want to try and figure out what's a p-value that's going to be sort of a very shallow curve here that's going to go through both roots because of this part of the equation, but then also force us through that one using p. So same kind of exercise. Here I've got my two roots of 10 and 11. Now let's plug in 4, 7, and let's solve for p. So I can divide through both sides by -7, or let's cancel the negatives first. So negative times negative is positive. Now let's divide both sides by 7. So that gives us 6p equals 1, or p equals 1/6. And then we can just preview it on Desmos. So you can see here roots at 10 and 11. And right now my p-value is 0.59. And as I move it, you see all the different parabola that go through those two roots. And we solved for this one at 1/6, which forces us through the point that we want. We could have done this differently. We could have just chosen a p. So let's just say p equals 1. And now we could have solved for a second root that makes our curve go through the place that we want. Oh, is that... Oops, sorry, that was our first root. Let's fix this. Okay, so we had a root at 10, and then I have this other root is at 1. Let's make a slider for it. So you can see as I drag my root back and forth, it's the curve still goes through my point at 10, 0. And the scale factor is always 1 because I didn't change it. It's just stuck at 1 here. But there's going to be some particular other root which is going to make that shaped parabola go through the other point we want. So we could have chosen it in the other order. We decided to arbitrarily choose a different root and then solve for p. We could have decided to arbitrarily choose a p-value and then solve for the other root that makes the curve go where we want. Why don't you time yourself on this and kind of see how comfortable you are applying these ideas. So it'll be just exactly the same as what I just showed you. So go ahead and make this the vertex and then solve for the scale factor that forces it through this point and tell me what that equation is. So step 1, I wrote the vertex. Step 2, let's plug in my other point. So I solved, I got p is -10/25, and there's the final equation. Let's do another one. Why don't you make this be the vertex now and solve for the p factor that takes you through that point. And remember the shortcut that I told you before. So this one I didn't need to calculate at all. I know that the x-coordinate is here at 3. I know that the y-coordinate of the vertex is 0. And then the scale factor, I know it has to be positive because I am going upwards here. But the exact magnitude is the same as the magnitude of this one because it's symmetric with this other parabola that we just solved for. Okay, last one. Go ahead and add another root at 10, 0, and this time solve for the p value that will take you through both roots, but also this point over here. Okay, so I started in root form. I got my two roots. Now let's plug in this other point to solve for p. So as you can see, I plugged in 8 for the x-coordinate, and I ended up getting p is -1, and so that would be the final equation.